So, we started the discussion about the solid phase transformations in the last class, and I said you that we cannot discuss all the solid to solid phase transformation during this course, but we are going to choose few of them and discuss. The first one which we will discuss is basically precipitation hardenable alloys, in which the precipitates forms from the solid solutions. As you know that this is a diffusional type phase transformation, because atoms needs to move because of the diffusional gradient, a compositional gradient, and form precipitates. This also involves nucleation and growth. So, we are going to discuss the first case, that is the eutectoid transformation. So, that is the precipitation transformations. Now, as you know, as I shown you that there are different alloys which this kind of phase transformations are possible. The one which is more predominant is the first one. Okay, this is the case of aluminum copper alloy or aluminum copper silicate alloys, and this is very widely used in the practical applications. So, we are going to spend most of our time on these kind of phase diagram alloys. So, before actually I discuss in detail, let me just tell you that this is a very common phase transformation observed in many alloy systems. It is not only limited to aluminum copper, but many alloy systems this is very common. To give an alloy, aluminum is obviously classic, and these alloys are used in the aerospace industry. The alloy which is named as 2024, these classifications are based on certain aspects which I will not be able to discuss, but these alloys actually contains copper, magnesium and manganese. You see copper content is about 4.5 weight percentage. Then we also have alloys like 6061 and 7075. 6061, well, in the 2024 basically the precipitated phase is S prime, as you see here is basically Al2Cu Mg. Normally in aluminum copper alloy it is Al2Cu and that is known as theta, but in the when you add little bit of manganese, a little bit of magnesium, not sorry manganese and magnesium both actually, manganese will be about 0.6% and magnesium will be about 1.5 weight percentage. The phase which forms as a precipitate is basically S prime, that has a composition of Al2Cu, a little bit of magnesium present, and it shows a very drastic change in the properties compared to aluminum. Aluminum has a yield strength about 60 MPa, whereas this alloy has yield strength about 400 MPa. That is like a huge increase. Similarly, 6061 is again an aluminum copper magnesium silicon alloy, and because it has a magnesium and silicon, the precipitate is basically beta prime, and this will be Mg2Si type. This also has reasonably good properties, but not as good as the copper, aluminum copper, magnesium, manganese. And 7075 is basically a aluminum zinc alloy with a certain amount of copper 1.6 weight percent, magnesium 2.5% and rest like manganese and chromium. So, these are actually three important aluminum alloys which show precipitation hardening behavior. But there are other alloys like copper beryllium, which is used in the mines. It contains about 2% to 8% of beryllium, a little bit of cobalt. Normally it forms zones, basically we will discuss about that. It has a very high increase of the mechanical properties. And then you have nickel and iron alloys. Nickel alloys are basically mnemonic, and it has cobalt, chromium, manganese, molybdenum, aluminum, titanium, carbon, little bit carbon. And the precipitates, we know that precipitates are basically Ni3Al type. It can be Ni3TiAl, Ni3Al type, and this shows fascinating high temperature properties. So, and finally iron carbon alloys or something known as maraging steels. They have huge amount of alloying elements, nickel, cobalt, moly, titanium, aluminum. It forms both sigma and Ni3Ti. Sigma is a hard intermetallic FeMO type or FeCr type, here is FeMO, and Ni3Ti, both these precipitates leads to huge increase in the yield strength and as well as UTS, and which you can see on the table. So these things clearly shows that precipitation hardened enamel alloys actually are the major class of alloys which are really used in the industry, and that I have been talking about to you for the last so many lectures, that phase transformation is not only a subject which is specifically dealing with basic aspects of the material science, but it has a lot of applications oriented important aspects which needs to be understood. Now so that means precipitation is a very common phenomenon in all these alloys, and whatever I am going to discuss is basically going to give you a snapshot of the picture. It is not possible to discuss everything in the time frame we have. As you know, aluminum, silver also form precipitates like GP zones. GP zone is a specific name which we will discuss today. Then you have theta, gamma prime and gamma, which is basically Ag2Al. Aluminum, copper, all of us must have some idea which we will discuss in detail. GP zone, theta prime, theta double prime, theta prime and theta. Theta is nothing but a L2Cu. Then you can have aluminum, copper, magnesium, aluminum, zinc, magnesium, which I have discussed. You can have aluminum, magnesium, silicon. So like here beta, eta, S or S prime. Copper, as you say, they are zones or gamma phase, and then other things like irons, carbon iron, nitrogen, or even nickel based alloys. So finally the precipitation happens in a sequence. The real crux of the slide is that precipitation does not happen from supersaturated solutions to directly to the equilibrium phase, but it happens in a sequence. That is what actually the tuning of the properties is very possible by looking at simply heat treatment sequence and microstructures. So as I said, I am going to discuss more in general about aluminum copper alloys, because that is a classic alloy system which shows precipitation hardening. And this is very important because all the theoretical backgrounds are basically based on the extensive study on this aluminum copper alloy. The alloy which is important and widely used in the industry is aluminum 48% copper alloy, shown here. So simply by adding 48% copper, we can actually change the mechanical properties of aluminum extensively. As you know, I have shown you the phase diagram. Aluminum copper phase diagram is basically very complex on the copper side. Aluminum side is not so complex. It has alpha phase liquid, and alpha is nothing but a solutions of copper in aluminum. It has a FCC structure with lattice parameter of 4.04 Armstrong. Now as you know, as I told you very nicely, suppose if I draw a dot as a vertical line here at about 8% of copper, what is normally done in the edge hardening? Let us first discuss about that. What is normally done is that this 8% copper aluminum alloy, that means it has 8% copper and 96% aluminum, is heated at about 500 and 550 degrees Celsius temperature, in the temperature range, and kept for certain time. So as you know, copper, which is basically a solute here, will be dissolved nicely in the aluminum matrix, and it will form a FCC solution between copper and aluminum. That is what is alpha phase. Now what is done is that from this temperature at about 550, this is quenched to, let us say, about room temperature, quenched into water. Normally room temperature is about 30 degrees Celsius. So it is quenched. So what will happen if it quenched, the alpha phase remains, because we did not provide enough time for the alpha phase to undergo transformation. Correct, alpha phase will remain in the sample because it has been quenched. Now once I take this quenched sample, this has basically quite a lot of copper, and then what alpha phase is supposed to have. If you look at carefully, I have shown you last class also, if I quench at room temperature, it should have, basically alpha phase should not contain large amount of copper. It should contain very small amount of copper. As you see here, this is the Solbas curve which is shown here. Solbas is going down like this, very rapid decrease. So at about say 100 degrees Celsius temperature, copper solubility in aluminum is negligibly small. So because of that, alpha phase will be basically quenching to water will lead to formation of supersaturated alpha, what is known as supersaturated alpha. Okay, so this supersaturated solution of alpha is not a stable phase thermodynamically, because it has large amount of copper than it is supposed to have. So once you heat up to 100 to 150 degrees Celsius temperature, these supersaturated alpha transform, and it transform in a sequence basically of phases. So what actually happens, supersaturated alpha will transform to alpha 1 plus GP zones. GP zones are actually the kind of a sheet of copper atom sitting on the aluminum lattice on the 001 planes of aluminum FCC crystal structure. So this actually copper atom which is 2 layer or maybe 3 layers of the copper atom sitting on the aluminum 001 planes, actually 001 planes, that is a Z axis planes. Now if you heat it up or keep it long time at 150 degrees Celsius temperature, for that again this will transform into alpha plus theta double prime. Okay, we will discuss about this structure theta double prime later. Then finally if we heat again and keep it at high temperature for more time, it has become alpha 3 plus theta prime, and finally it will produce alpha 4 plus theta. Theta is nothing but at a composition of Cul2. So as you see here, these alpha 2, alpha 1, alpha 2, alpha 3, alpha 4, they are actually same alpha but different concentrations of copper. Why? Because as these phases form, this is GP zones, theta prime, and finally theta, which is a basically incoherent precipitates having a body center tetragonal structure, it takes out the excess copper which is there in the supersaturated alpha solution. If you remember carefully, we have quenched the sample from high temperature to room temperature and retained huge amount of copper in the crystals in the sample, and this copper which is present in the alpha phase is not cannot stay there longer because it is a metastable phase. Because of that, it will come out as you heat it up or give sufficient time for the diffusion happen, because we need to provide temperature and time for the diffusion of copper atoms in the sample, and this leads to formation of these precipitates. Now one can actually discuss in a detailed manner, okay, that is what I have shown you here. As you have seen that these different phases like GP zones, theta double prime, theta prime, all these things, what are they? Let us look at them very clearly first. Okay, as I said, GP zone is nothing but a specific copper atom sitting along 001 planes of aluminum. What is this? Let us look at first aluminum matrix. This is the alpha matrix. You see it is nothing but a FCC aluminum. Basically it is not FCC aluminum anymore because there is a lot of copper inside it. So therefore all the atoms which I am showing here as these blobs, okay, they are shown as aluminum even in the books also, but all of them may not be aluminum. There will be some of our atoms will be copper, okay, and it has a lattice parameter of about 4.04 Armstrong. Now if you see carefully, this is nothing but a segregation of the copper atoms along certain planes, and these planes happens to be these planes, that is 001 planes of the aluminum alpha crystal, and they actually form some layers, maybe 2 layers or 3 layers, okay. That is what is shown here. You see these are the copper atoms sitting as a layer, and because of that it forms very distorted structure in the lattice, and therefore these are actually known as zones. In fact, these were discovered by Gunier and Preston simultaneously while analyzing the X-ray diffraction patterns of these alloys. The X-ray diffraction pattern shows streaks in the patterns, and looking at the streaks they concluded that such a kind of zones actually form during the first step of precipitation of aluminum copper alloys, and that is why this is named by their name GP zones, G for Grunier, P for Preston. Now what happens, this is the first So, alpha transform to GP zone, alpha superscript solutions are transformed to GP zone first. Now, once if you keep it for long time, then it will first transform to theta double prime. We will discuss later why it is first from GP zones, then theta double prime, then theta prime and theta. First let us look at crystal structures of that. As you say, it is shown, theta double prime is shown like a, it has again A is about 4.04 Armstrong and C is about 7.68 Armstrong basically. So, importantly it's basically the 001 planes actually remain almost similar. Okay, you see here FCC. Okay, only in between we have alternate layers of aluminum. You see here, this is aluminum, this is aluminum, this is aluminum. Okay, and it's very evident after looking at all the microstructures that all the sides of the theta double prime remains coherent with the matrix. Please go back to our lectures, my lectures on interfaces. So, coherency means is basically it remains almost completely coherent along the all sides. That is what is shown. All the planes of that 001, 100 and 010 they remains coherent. That is why they actually dissipate. Now, once this theta double prime transform to theta prime, okay, again is C axis changes, A axis does not change. Remember, A and B actually remains 4.04 Armstrong, C becomes 5.8 Armstrong. Because of that, because of these transformations, okay, so some of these planes remains coherent. It is obvious because A and B remains same, the lattice parameters. So, therefore, 001 planes actually remain coherent, or in extreme case it will be semi coherent. There will be some distortion of the planes, but these planes, that is 100, this plane 100 is these sides, and 010 they become not coherent, they become actually incoherent because of the copper atoms nicely sitting on these places. Now, what is theta then? Theta is basically equilibrium precipitates. It has a body center tetragonal structure. As you see here, it is not a very simple structure to analyze initially. It has a lattice parameter of 6.07 Armstrong A or B, and C is about 4.87 Armstrong. So, what is happening when you transform theta double prime to theta is basically C axis is changing, but when it becomes theta, both C and A axis values, the A lattice parameter values are actually changing, and it becomes completely incoherent with the matrix. Now, if once you have analyzed these crystal structures and atomic positions in these pictures, it is very evident why theta cannot precipitate directly from the alpha supersaturated solution. That is mainly because of the incoherent natures with the precipitate and the matrix. The interfacial energy is very high. So, nucleation barrier becomes very high. Remember, nucleation here in a solid state has two important aspects. One is the interfacial energy, other one is the strain energy. Because of the interfacial energy is very high for the theta, because theta is incoherent precipitate. So, therefore, interfacial energy between the precipitate and the matrix alpha is very high. Not only that, it will also strain because of the difference in the elastic properties. There will be a lot of strain built up, and these two aspects will lead to higher nucleation barrier. That is why it is very difficult to precipitate directly theta from the alpha supersolids solution. On the other hand, if you look at GP zone, it is basically completely coherent structure. GP zone is nothing but segregation of the 2 to 3 layers of the copper atoms on the 001 planes of the alpha, and because of that, because it is basically few layers, the interface remain coherent, the strains do present, but they are very low, because few layers of copper, although copper and aluminum atomic size are different, it will not distort the lattice so much that the strain energy will be high. So, therefore, although there will be strain, but strain energy will be, elastic strain will be low, and interface energy is obviously low because it is coherent with the matrix. Because of that, its nucleation barrier is very low. this will be followed by theta double prime. Again, if you look at theta double prime, only all the sides are coherent. I have already discussed. Because of the nature of the coherency, the nucleation barrier is slow. Only thing which will be increasing from GP0 to theta double prime is the strain energy between elastic energy between the precipitate and the matrix, and so on. Theta prime will have some of the facets are basically incoherent. So because of that, something the surface energy, interfacial energy will increase, and for the theta is basically is very high interfacial energy. So this actually leads to sequence of precipitation, and one can actually explain this sequence of precipitation using field energy constructions. That is what is shown here, G versus XU plots. This is directly taken from the book of Porter and Sterling. As you see here, this is my field energy curve of the alpha supersaturated solution. Okay, because GP zone is not a distinct phase, so therefore we cannot show as a Bessel field energy curve for that. It is nothing but extension of the field energy curve of the alpha. Remember, GP zone is nothing but a few layers of the copper atoms on the 001 planes of the alpha. So therefore, if I draw a common tangent between GP zone and this alpha, what I see that it cuts at alpha 1 here and it cuts there. So GP zones will have quite a lot of copper. As you see, concentration of copper is high here. That is because a sheet of copper layers basically getting attached. But the alpha which is in equilibrium with the GP zones has a composition which is higher in copper also. So, and the energy difference between this alpha and the GP zone mixture compared to alpha, this is alpha and this is this common tangent will tell you the energy of the system consisting of alpha 1 and GP zone given by this point is basically G0, which is very small. So that will be easy to transform from alpha supersaturated solution to alpha 0 plus GP zone. Okay, it should be alpha 0. I should have written it like that, then it helps you. Okay. Now if I again do it same thing for the theta double prime, theta prime and theta, obviously all of them will have separate field energy curves because they are separate phases. Their lattice parameters are different. So if you see a theta double prime, I can always draw a common tangent between alpha and theta double prime and get the composition of these and these. Theta same thing, theta prime also similar things, and the field energy is gradually decreasing from G0 to G4. So system actually can reduce its energy. So alpha supersaturated solution can reduce its energy by in sequence by forming GP zones theta double prime and theta. This is possible, and that is why this transformation happens. One is the kinetic barrier, that is the nucleation barrier. Other one is the energy decrease happens in a step manner. That is much easier things to happen. Now let me just show you some microstructure before I end this part of the lecture. As you see, this is the microstructure of GP zone, the first one, GP zone. Why? Because they are actually very thin layers of the copper attached to the alpha. So that is why they show only strain contrast in the transmission electron microscope. They do not show a precipitate like morphology, they show a strain contrast because it is coherent to the matrix. Only thing is difference between the phase GP zone and the matrix is the strain developed. Similarly, if I go to theta double prime here, this is theta double prime, okay, or let us write here theta double prime. Theta double prime basically it is coherent in all the three 001 planes, and they look little bigger, and you see this is one theta double prime, this is another one, okay, they are dish shaped. But the moment it's become transformed to theta prime, they become long. You see here, this is the one, that is another one, okay, and that is another one, you see. And you see there are a lot of strain contrast, spin contours and other things are present. And this is theta. Theta has a very specific shaped precipitates, it's a long dish shaped precipitates. So that's how actually the step happens, GP zone to theta prime theta double prime to theta and theta double prime, theta prime, sorry, this is theta prime, okay, to theta. That's always happens in the microstructures. Now if you look at nucleation, nucleation of these phases happens normally at the defects in the microstructures, mostly the defects in the alpha grains. This is the nucleation of the theta double prime on a dislocation, okay. You see here these are the theta double prime, they are forming a dislocation, and there are a lot of precipitates present in the matrix also. On the gain boundary normally precipitation happen more frequently. This is a gain boundary of the alpha, theta has precipitated on the gain boundaries. This is another boundary between two alpha grains, both you can see theta and theta prime has precipitated. So nucleation also happens heterogeneously on these gain boundaries, interfaces or dislocation structures. This is also I have discussed in the last few lectures earlier. And this is basically the naturally observed in the aluminum copper alloy, these precipitates. And remember these precipitates actually block the motion of the dislocations or causes barrier to the motion of dislocations because they are present in the matrix. So whenever we try to deform these alloys, the precipitates actually allow us to basically make the alloy strong, very high strong, in the sense that they basically they act as a barrier to the dislocation motions. We will discuss more about that in the next lecture. So that's in a nutshell is the precipitation in the aluminum copper alloy.